So now we're going to talk about the electrical activity of the heart. So the electrical activity is going to be controlling which cells contract and when. I got a chat from you guys. Just been notified that the outlines for this chapter aren't up yet. I'll make sure those go up right after class. Okay, so we're looking at the electrical activity of the heart because depolarizations in the heart are going to be controlling when that heart muscle contracts. So just like we used depolarizations as signaling in our neurons, we're going to be using depolarizations as signaling within the heart itself. Okay. These were our two previous questions. Okay. So we're trying to figure out how this electrical activity in the heart works. Okay. So a cool thing about the cells of the heart is that they have this property of autorhythmicity, which is to say that they can generate their own rhythm, so they can generate their own depolarizations automatically without nervous input. So we're going to see that we have cells that create electrical activity at specific paces independently of anything else. So if you put these heart cells in a petri dish, they would still create this electrical activity. It's really neat. And we saw that once before, very briefly, when we were talking about smooth muscle. It had some spontaneous depolarizations. This is like a really intense version of that. This is what controls the beating of our heart. So when we're thinking about our autorhythmic cells, we're going to have basically two types. We're going to have cells that we call pacemaker cells. Those are the cells that are actually going to be setting the pace of the heartbeat, and they're like pulsing. And then we're also going to have conduction fibers. So in order to have the muscle cells actually contract, we don't need to just have this electrical activity. We also need to be able to spread it throughout the heart, and we need to spread it in a specific order, right? Because we want our atria to contract, and then we want our ventricles to contract. So we need to send the signals first to the atria, then to the ventricles, in order to get this order of contraction of our heart chambers. So we're going to have these cells creating their own rhythm. We're going to have cells that create a pathway for this electricity to flow through the heart. So for the next couple slides, we're going to be distinguishing our pacemaker cells, those ones that are setting the pace, from our conduction fibers, which are the ones that are allowing the signal to travel. They're conducting this electrical signal. They're like our wires. So the pacemaker cells are going to be spontaneously depolarizing. And joy, oh joy, we're going to look at the ions responsible in a little bit. So they're going to be changing their membrane potentials by changing membrane permeability to specific ions. And we remember from before that when this happens, when we change which ions can travel in and out of the cell, we can generate an action potential. So these pacemaker cells are generating action potentials. And they can therefore coordinate and provide rhythm to the heartbeat by setting the pace of those action potentials. So how fast we have action potentials is going to determine how fast the heart beats. The conduction fibers do have a little bit of this property as well. They can, in very extreme cases, create a heartbeat if everything else fails, but their real job is to rapidly conduct those action potentials. So they're just going to be specialized for sending those action potentials throughout the heart and getting it to the rest of the myocardium. Myocardium specifically referring to the heart muscle, right? Myo, muscle, cardium, heart. So here are the names of the cells that we want to be thinking about. When we're thinking about the pacemaker cells, You're going to be thinking about something called the sinoatrial node, SA node for short, easier to remember. Sinoatrial refers to where you would see it in the heart. There's a sinus, which is basically a collection of venous blood. You don't need to worry about that. But they're in the atrium. The atrial part does help us. The SA node is in the right atrium. It's the pacemaker of the heart. It's basically going to be beating the fastest, which means that it's going to override any other electrical activity in the heart. But we'll also have a really important site of electrical activity that's kind of like our backup, something called the atrioventricular node, which is going to be found between the atria and the ventricles. So we'll also refer to it as our AV node. Our conduction fibers are going to allow these electrical impulses to travel between our different groups of pacemaker cells and out to the myocardium. So first, we're going to see something called our internodal pathways. The internodal pathways are going to go between our two nodes. So they're going to travel between the SA node and the AV node. We'll also have something called the bundle of His. Weird name, but the bundle of His is basically going to split out from the AV node and start to send those fibers down to our ventricles. We're going to squeeze those ventricles from the bottom of the heart up. The bottom of the heart, the part that's, down towards your abdomen, is actually called the apex because it's pointy. So we're sending that electrical signal down to the apex of the heart, which is at the bottom. And then we're going to send it back up. So we're going to have these Purkinje fibers that then spread and wrap around. We're going to take a look at this in pictures, and we're going to take a look at a short video as well. I do want to talk a little bit more about what I briefly mentioned about the SA node setting the pace, but having other points that are able to take over. So when we're looking at our autorhythmic cells, they each have a speed of these action potentials that they give off. So they each have this pace, and it's distinct depending on which cells we're talking about. It's basically what I'm saying. So the SA node fires 70 to 80 action potentials per minute, which if you'll skim this list, it's the most action potentials per minute. It's the fastest. So the SA node is going to be controlling the heart most of the time. The AV node is a little slower. So it fires off 40 to 60 action potentials per minute. The reason that's not in control, right, is that whenever it receives an action potential coming from the sinoatrial node through those internodal fibers, it basically interrupts the action potential that it's trying to get going. So as soon as it has a signal from the SA node, it's like, oh, okay, we'll do that. And because it keeps getting these signals pretty quickly from the SA node, that SA node is in control so long as the SA node is functioning normally. The bundle of His and the Purkinje fibers, so two of our conduction fibers going down through the ventricles, could also fire, but they're really slow, 20 to 40 action potentials per minute. So that really wouldn't be enough for your heart to function, and it's overridden by both the SA node, or if the SA node fails, by the AV node. When we're thinking about the muscle cells in the heart, the cardiac muscle cells, we're going to see that they're all linked by gap junctions. So as we're sending this electrical signal through the heart, the electrical signal is just made up of ions, basically, right? So we've thought about ions. In this case, we're going to be thinking a lot about calcium, right? Because we're thinking about muscle, but sodium is there too. Sodium will play a role, so will potassium. So because these cardiac cells are linked by gap junctions are like holes in the membrane connecting cytoplasm. So whatever ions are in the cytoplasm of one cell just flow directly into the cytoplasm of the next cell. So these cardiac cells linked by gap junctions all communicate with each other because whatever happens to the ions in one happens to the ions in the next. Okay. So the rule for when we're looking at these autorhythmic cells, if we're thinking about pathology or something going wrong with the heart, is whatever the fastest depolarizing cells left are, those are the ones that are going to control. So under normal function, SA node is in control. In pathological conditions, we might have one of these other centers taking over. So fastest cells are considered our pacemaker for the heart. They set the rate for the rest of the heart. You can immediately see, right, like what an actual pacemaker does here, right? It's an actual pacemaker, like the device, and it takes over this role, right? If we have chronic issues with, for example, our SA node, right? If we can see that it's failed before and we're worried about it failing again, we can put in a pacemaker that creates external to the heart kind of electrical signals and kind of jump starts the heart when this autorhythmic signaling fails. Okay. So the way that we want our heart to contract, right? We want this excitation to spread throughout the heart so that the atria contract, which sends blood to the ventricles. Then the ventricles contract, sending blood to the lungs and to the body. So this is going to be coordinated by the fact that we have gap junctions spreading the depolarization. We have these conduction pathways sending this signal, kind of speeding along to the places where we want it. So speeding along from the atria to the bottom of the ventricles to the apex of the heart and then back up. Okay. We'll also note that a special feature of cardiac cells are something called intercalated discs. These are junctions between adjacent myocardial cells. So they're actual physical cell junctions connecting the muscle cells in our heart. And they're specialized for resisting mechanical stress because the forces involved here are really strong. We need blood to go through the whole body, right through the whole systemic circuit. So we'll see junctions called desmosomes, which are a specialized type of anchoring junction. I don't know how much you guys have thought about junctions in a while, but just know that those ones are there to resist mechanical stress. Our gap junctions, which we have talked about a little bit more length, are there in order to allow for electrical coupling. So really to allow these electrical signals to travel through the heart. So we can see what these look like. So here we see an example of our SA node, right? So we'd have our pacemaker cells, our autorhythmic cells here. Here we see some muscle cells. So we can see that we have signal traveling, right, through them. The intercalated disc is like this kind of zipper looking structure, this zigzag. So if we zoom in close to this intercalated disc, see one thing it has is a gap junction, allowing this signal to travel. So our electrical current is traveling through this gap junction because the electrical current is really just ions. Our intercalated disc also has this special structure kind of holding together our cells really tightly, giving them physical support. So here we see our desmosome creating that physical support for our myocardial cells. Okay. So we're going to see conduction happening in a specific order. So we're going to initiate a signal, we're going to conduct it through the heart and through the muscle. So the order for this is that our action potential, so AP is here, our action potential is initiated in the sinoatrial node, the SA node. The signal first spreads through the muscles of the atria, so the right and left atrium, small kind of at the top of the heart, so top physically up kind of towards your neck, which unfortunately we would call the base of the heart anatomically. Okay, so they're spreading through the atrial muscle, through some interatrial pathways. They're also sending that AP, that action potential, to the AV node via the internodal pathway. So when the SA node ends off its electrical current, one of the places it's going kind of fast on this internodal pathway, acting like a highway, is to the AV node. We described the slight delay in firing between the SA node and the AV node, the AV nodal delay. So there's a slight difference in when the SA node fires versus when the AV node fires, because there's a little bit of a gap in the time that that electrical signal takes to get there. Then we have our signal going through the atrioventricular bundle, which is also called the bundle of His. So those are the same thing as bundle of His on previous slides. So maybe let's stick with that. So that's going out from our AV node into the ventricles, splitting into left and right bundle branches. So this bundle of His is going to split into these bundle branches, one which goes to the right heart, the other which is going to go to the left heart. So we're contracting both of these ventricles. Then we're going to have the Purkinje fibers wrapping around. Finally, we'll take a look at pictures of what this looks like. I always find pictures helpful. Hope you do too. Okay. So what we're looking at here is the right atrium. We can tell it's the right atrium because that's where venous blood comes, right? The first place that blood goes into the heart is into the right atrium. So here we can see the superior vena cava. We know this is the right heart. The sinoatrial node, the SA node, is right here, basically right where the vena cava is coming in. So up here at the top of the right atrium. The internodal pathways spread down to the AV node, which is located basically right here at the bottom of the atrium. It's kind of in the center of the heart almost. We'll see that the signal is going also to the left atrium. We want that to contract as well, but it's going faster through these internodal pathways. So when we're tracking the order, we want to talk sinoatrial node, internodal pathway, AV node. Okay. So our AV node, located right here, all right, not in the ventricles yet, but right above. So that's going to receive our electrical signal next. Here we have the bundle of His. So the bundle of His reaches down into this wall between the ventricles. So we'll call this later our interventricular septum, but you don't have to worry about that until anatomy, and it doesn't come up till A&P2. So right now, just know it's going down here between the ventricles. Here's our AV bundle or bundle of His. We can see it splitting into the right and left bundle branches. All right, now we've got two. You can see how they're traveling down to the apex of the heart, this pointy part, right? Here at the bottom, the apex. That's because we want to contract these from the top, swoosh up into these vessels. The Purkinje fibers are letting us do that, right? So as we follow these right and left bundle branches down, we can then see that they start to wrap back up. We have these smaller fibers going around the whole ventricle, allowing the whole ventricle to contract. So this is going to give order and structure to our heartbeats. It's going to help with this blood flow from one location to the other in a specific order, right? So we want everything to travel in a series from the right atrium to the right ventricle, out to the lungs, to the left atrium, to the left ventricle. These electrical currents are going to allow the atria and ventricles to contract in the appropriate order. So we're gonna take a look. The guy in an ambulance telling us about this. So now I gotta make sure my sound is shared with you guys. Hold on a second. Now I've muted everything. There we go.
So now we're going to discuss the cardiac conduction system and its components. This is a deeper dive into the biomechanical and electromechanical actions of this incredible organ called the heart. So now let's take a closer look at the heart and how it functions as a circulatory muscle. You see, the myocardium is the muscle that's unlike any other muscle within the human body. It's unique in that it can generate its own electrical impulse, known as automaticity. A special part of the heart, located in the superior aspect of the right atrium, called the sinoatrial node, or the SA node for short, works like an internal dynamic pacemaker. This internal pacemaker, when the heart is working correctly, generates an electrical impulse that then travels through the myocardium in a very organized and deliberate fashion. You see, this SA node generates an electrical impulse at about a rate of 60 to 100 times per minute. Now let's follow that pathway of the electrical impulse from the SA node to where it terminates at the end of the Purkinje fibers. So after the SA node initiates that electrical impulse, that impulse travels via the pathways called the internodal pathways. These travel throughout the right and the left atria, and then depolarizes the myocardial cells, which causes the actual muscle in the atrium to contract. From the atria, the electrical impulse travels along the pathway to the atrioventricular or AV node, where it may be delayed strategically before it moves through the bundle of His and ultimately to the Purkinje fibers, which travel down through and wraps around the ventricles, completing the electromechanical cycle of a complete heartbeat. See, the delay in the AV node, which is located in the left lower wall of the right atrium, is a necessary process in order to allow the ventricles to beat independently of each other, and thereby they operate as a double pump action. If for whatever reason the SA node does not operate properly as the primary impulse generator or pacemaker, the AV node then can begin sending its own electrical impulse instead. Though the AV node can generate its own impulse, it does so at a slower pace, which ranges between 40 and 60 impulses per minute. The impulse generated from the AV node then travels through the bundle of His, which is the route that the impulse travels to reach the Purkinje fibers, which wrap around those ventricles we talked about earlier. This ventricle contraction then circulates the majority of the oxygenated blood throughout the body. The bundle of His is the route of electrical transmission which travels between the atria and the ventricles. Now, after the impulse reaches the bundle of His, it travels down the length of the interventricular septum and leads to the left and right bundle branches, of which the left bundle branch has 2 fascicles because the left ventricle is larger than the right ventricle. These bundle branches terminate into the Purkinje fibers, which depolarize the ventricular cells and cause the ventricular muscles to contract. In the case that both the SA and the AV nodes do not generate electrical impulses properly, the Purkinje fibers, which are located within the ventricles, then become the primary pacemaker source, which only generates electrical impulses in the range of around 15 to 40 beats per minute. Usually, this is too slow to produce an adequate systolic blood pressure or oxygenate cells within the body.
So now we're going to think about the ionic basis here of the electrical signal. Okay. So we have these pacemaker cells, and our autorhythmic cells, right, they have their own action potentials that they're creating. We're going to call them the pacemaker potentials. These are due to changes in the permeability of the membrane to different ions, just like when we were looking at nervous cells. Except in this case, these are just happening on a kind of automatic cycle. So what we're going to see happening is that we're going to see our potassium channels closing. So remember that Potassium wants to escape from the cell. So whenever potassium is leaving the cell, a cell becomes negative. So in order to depolarize, we close those potassium channels to kind of trap the positive charges in. Remember that as our membrane potential gets more positive, that's what a depolarization is. Okay. So in order to actually get that membrane potential up, get it to start inching up, we're going to open two types of channels. So we're going to be opening sodium channels, we're going to be opening calcium channels. So we're going to see that this happens in specific orders in different types of cells, what the role the sodium versus the calcium and the potassium are going to play. In order to get to the threshold, we're going to see that we're using a lot more calcium in the heart than we were in our neurons. In our neurons, the story was really about sodium. We're going to be thinking a lot about calcium here, basically because we're thinking about muscle, but also just that's how heart cells work. So we're going to see that we have both fast and slow calcium channels. We're going to have these fast calcium channels creating a lot of this action potential. And then we're going to see that repolarization at the end of this is due to opening those potassium channels back up again. Positive charges escape the cell, pulling the membrane potential back down, repolarizing us to our resting potential. We're going to have some graphs to look at here. Okay, so what we're looking at here is the membrane potential in our pacemaker cells. And we're looking at it first in phases of basically depolarization. And then at the bottom, we're looking at what permeabilities are changing. So what we see happening here with our action potentials in our pacemaker cells, so you see that we start off with a slow depolarization. So here in kind of purple. Then we have a rapid depolarization causing a spike. That's our action potential. This peak, this rapid depolarization. And we repolarize and come back to our resting membrane potential. Okay. So just like with the neurons, we also have a threshold. We're not going to really worry about numbers here. But we can see that this peak looks pretty similar to what we've seen before. So the permeabilities that we're talking about are a little bit different than when we were talking about neurons, but we see a role for a lot of our familiar players, right? So the colors don't match up great, but basically these are in order. So this first segment is supposed to be orange. This second segment here is yellow. Then we got green. Then we got this pink purple. Okay? So that's just explaining the key versus this picture. All right, so what we have happening first is our potassium permeability decreases. So we don't have the outflow of positive ions. So we're like stopping ourselves from becoming negative. We're increasing our permeability to sodium. That's what we saw in neurons, right? So we know sodium wants to flow into the cell, so become a bit more positive. So that's this first part of the depolarization. What happens next is that we start to turn on the calcium permeability. So we haven't talked that much about numbers with calcium, but it happens to be the case that the equilibrium potential for calcium is positive, just like sodium. It's actually 130 millivolts. So it's very, very positive. All of which is to say that when you open a calcium channel, calcium wants to flow into the cell. So here we start to close our sodium channels, but that's okay. We're going to keep depolarizing because we're opening calcium channels. We then see calcium channels really, really shoot our membrane potential up here. So we have another type of calcium channel open, basically. We're not going to worry about the different types of calcium channels for the purposes of this class. And then we have our repolarization. Our permeability to calcium starts to decrease. These calcium channels are closing. Our permeability to potassium is increasing. We're opening up those potassium channels again, allowing potassium to flow out of the cell, pull us back down to its very negative equilibrium potential. Questions about these graphs before we move on to what's going on in the cardiac cells as opposed to the pacemaker cells? Okay, so that was a pacemaker cell, but we get a little tricky in the heart, right? Because we have a number of different types of cells that have to have this action potential going through them so that we can have the heart contract. So we're also going to look at the electrical activity in the contractile cells of the heart. So those muscle cells with their actin and myosin, their cross-bridge cycling, that are actually contracting in order to contract the atria and the ventricles. So these are going to have 4 phases of permeability and activity. So the first phase is that they're going to increase their permeability to sodium. So that's just like the pacemaker cells, just like our neurons. Next, they're going to decrease their permeability to sodium. So that's like half of what was going on in our second step of the... Sorry, everybody, my internet is not awesome. Okay, so we were looking at the cardiac contractile cells. So they start out by increasing their permeability to sodium. Sodium flows in, they depolarize a bit. Then we shut off this sodium signal. Okay, so we're decreasing our permeability to sodium. Then we increase our permeability to calcium. So we're going to allow calcium to flow into the cell while stopping potassium from flowing out. Then we're going to see that we're going to start letting that potassium flow out, stop letting calcium flow in, and we're going to return to our resting membrane potential. Now, cardiac contractile cell action potentials, basically the amount of time that they're contracting, is much longer than skeletal muscle. So that's just the thing to know is that this takes longer. So it will have a longer contraction for these fibers. We are going to look at this on a graph because based on that list of steps, honestly, I'm not sure this is what you would have drawn. So we'll take a look at how this maps on to the membrane potential for those contractile cells, right? So this isn't the pacemaker cell anymore. This is the heart cell that's contracting. Okay, so this step 0 is increased permeability to sodium. So here we actually see that our membrane potential changes super significantly during this step 0. Right, so we have rapid depolarization with this first step in our cardiac muscle cells. This number 1, this phase 1, decreased permeability to sodium. We actually do see a brief repolarization happening there. So we can see that the membrane potential is going down a bit now that sodium's not shooting in anymore. Phase 2, the increased permeability to calcium combined with decreased permeability to potassium basically leaves us with this kind of plateau. So we're not falling anymore very much, but we're not really having enough calcium coming in here to depolarize us again, just to slow this escape here. And third, once we don't have calcium coming in anymore, and we really do open those potassium channels, we have major repolarization, right? Like actual repolarization. We go down and we come back to our resting membrane potential. So for the membrane potential here for these cardiac cells, I have sodium playing kind of a bigger role versus calcium playing a bigger role in the pacemaker cell. So we'll try to touch on this again once or twice. We're going to have, honestly, a lot more graphs in this section than previously, but just note that this is a little different than what we had going on in the pacemaker cells. Okay. So just like in our skeletal muscle, we have excitation, contraction, coupling when we're thinking about the heart. Remember that excitation, contraction, coupling just means we're matching up action potentials to actual contractile activity, so actual contraction of muscle cells. So this is going to work honestly pretty much the same as in our skeletal muscle. We're still going to have T-tubules. We're still going to have calcium coming from the sarcoplasmic reticulum. We're still going to have this relationship between troponin and tropomyosin. But there will be a couple of features that look a little more like smooth muscle. We didn't really talk about the details of excitation, contraction, coupling, and smooth muscle, although your textbook did. But the properties that are similar to smooth muscle instead of to skeletal muscle are that a lot of this conduction is going to be happening through gap junctions. And we're also going to see that not all of the calcium for contraction is coming from the sarcoplasmic reticulum. Some of it is coming from the extracellular fluid. I'll go ahead and take a look at that. So this is the big hole diagram, but we're going to talk about it in steps. So we're going to start here with number 1. As a depolarizing current comes through a gap junction from a neighboring cell, possibly another contractile cell, but possibly an autorhythmic cell. So maybe one of our conduction fibers, for example. Okay. So we have our depolarizing current. So our electrical signal, our ions coming through. When we're talking about how this links up with the actual contraction of that cell, you're going to see that this action potential is traveling along the plasma membrane, down those T-tubules, just like it did in our skeletal muscle. This is going to trigger calcium to come out of the sarcoplasmic reticulum into the cytosol. It's also going to trigger calcium channels on the plasma membrane to open. Okay? So we have calcium flowing into the cell, and that was part of the electrical activity of the cell, but it's also part of why we see contraction here. Right? So calcium does both. Calcium binds to troponin. Troponin pushes aside tropomyosin. This is exposing our myosin binding sites. So then we start to see our cross-bridge cycling, just like in our skeletal muscle. Right? So we have these cross bridges forming. We're pushing on the actin with our myosin. We're making our cells smaller, right? We're shortening this muscle fiber, causing contraction. This ends when calcium is reabsorbed into the sarcoplasmic reticulum or pumped back into the extracellular fluid. So since some of this calcium came from outside of the cell, some of it is going to go back to the outside of the cell. Finally, now that we don't have calcium anymore, tropomyosin is going to block those myosin binding sites over. Our cross-bridge cycling will cease, and our muscle fiber is going to relax. Okay. So then we're back to our normal length of that muscle fiber. So that portion of the heart is at rest again. It's in its relaxed state. Okay. So this slide is just noting the different ways that calcium is removed from the cytosol. So this first one is familiar from the skeletal muscle, that calcium is being reabsorbed into the sarcoplasmic reticulum. So calcium ATPase. ATPase just means a pump, right? We're using ATP to do something. So we have calcium being reabsorbed using a calcium pump into the sarcoplasmic reticulum. But this is pointing out that we're also sending calcium out of the cell. One way we're doing that is with just a plain old calcium pump. Another way we're doing that is that we have a sodium calcium exchanger in the plasma membrane. Troponin and tropomyosin do their usual things, are covering up those myosin binding sites on the actin, stopping cross-bridge cycling, relaxing our muscle fiber. Okay. And I'll finish up with these polling questions. Why not? Okay. Awesome. Okay, great. So we should be thinking about our pacemaker cells and our conduction fibers. Now, that's what's controlling and coordinating our heartbeat. I think we got another question. Yep. All right. Other question is, where are our nodes? Okay. So a little more than half. Yes, our atrioventricular and sinoatrial nodes are our pacemaker cells in the myocardium. Most importantly, our sinoatrial node, but also our AV node. Okay, that is it for today. And next time, take a quick look at an EKG or ECG before we move into our next topic.